Hello and welcome to my presentation at hand, held first on INTES Tech Meeting on April 22nd, 2021. My name is Gerhard Nötzel-Steidle from INTES company in Stuttgart. This presentation is a summary of some current studies that are dealing with the PERMAS capability to handle highly nonlinear structural behavior. I want to show you the nonlinear static capabilities of PERMAS by means of three realistic applications, in brief and more in detail. These are a rubber sleeve, a door window seal, and a rubber fender. The nonlinear static response of structures starts from an initial state and ends up in a finally displaced state. Nonlinear behavior might be visualized simply by macroscopic nonlinear response curves. For the first application, the mechanical task is to invert a rubber sleeve, resulting in large deformations. In second example, to wind up a side door window, resulting in large displacements. And in third example, a ship bangs into a rubber fender while it is docking, resulting in very large strains. Possibly nonlinear behavior is in general expected in all real structures and hence more and more covered in the analysis features of nonlinear PERMAS. Have a first look on three aspects of these features. Large structural deformation requires to consider geometry updates and contact updates. Nonlinear material behavior, like hyperelasticity, leads to large strains. And a nonlinear analysis needs appropriate element discretization, prescribed displacement loading, and adapted time step increments to simulate even a decline of global stiffness. Coming to the application examples more in detail. The first example is a rubber sleeve which is similar to rubber bellows or other sealing members. The mechanical task is to invert the shape of the rubber sleeve. For the simulation, a quarter model is sufficient, with two symmetry plane boundary conditions. All nodes on lower surface are supported in vertical direction. The upper edge nodes are controlled and loaded by a prescribed displacement along the vertical z-axis. 4 different models were studied, using linear or quadratic hexahedral elements with a fine or coarse mesh. The hyperelastic material is considered as neo-hook type material, with 2 parameters for strain potential. To easily compare hyperelastic with linear elastic material, the stress-strain curve is linearized at small strains and could be checked in PERMAS RES file protocol during the analysis. Coming to the results. Let's have a look on the macroscopic reaction force displacement curves for the different meshes. A coarse or fine mesh with quadratic and a fine mesh with linear hexahedron elements show almost the same reaction force result. See the solid lines. A coarse hexahedron mesh with 2 linear elements over thickness is not appropriate to represent the internal bending stress through the wall thickness of the sleeve. See the dotted line. The animation shows the development of deformation and equivalent total strain over increasing displacements. Starting with the first local maximum, we have another increase in force to a second maximum, and then a breakdown of stiffness. Some findings and lessons learned. An appropriate mesh with adequate mesh size through the model thickness is necessary to represent a correct strain and stress distribution due to bending. 2 elements of quadratic order or 4 linear elements are sufficient through thickness. Discretization in circumferential direction is secondary and should have a good element-edge ratio only. The structural deformation is simply 2-dimensional and shows only one main curvature in vertical direction. A fine mesh with linear solids of hexa 8 type or even a coarser mesh with quadratic solids of type hexa 27 shows correct and very comparable results. An inappropriate mesh size will show inaccurate results for local deformation and parts of global response. Let's have a look on the second application. The second example is a door window seal. The mechanical task is closing a car side window to seal the car against strain, resulting in large displacements of the window glass and therefore changing contact partners. For the simulation, a complete model is considered. Both sealing lips are connected to base material mounted on car structure. We consider normal contact between glass and sealing, optional with friction. The window glass is mounted and controlled by a prescribed displacement of 2 wind-up points along a guiding curve. During loading, the glass moves in vertical z-axis. The hyperelastic material is considered as Muni-Rivlin type material law, with 3 parameters for strain potential. The model characteristics give some numbers for model size and computational effort. Coming to the results. Let's have again a look on the macroscopic reaction force displacement curves for inside and outside sealings. By the way, reaction forces on the mounted base are opposite to the contact forces between glass and sealing. Please recognize, during the first about 10 mm, the glass gets into contact with the first and then with the second sealing lip, becomes centered and then pushed through the sealing gap. Friction between glass and sealing reduces lateral reaction forces. Please have a look on the development of total strains and the contact force vectors. First, in an overall view on side window. Here at the beginning we have a finding of contact and then the glass is going through the ceiling gap. And here in an enlarged view on the ceiling lips. In the door window seal model, an appropriate mesh needs adequate mesh size in the section of the seal. Mesh discretization in longitudinal direction is again secondary and needs good edge ratio only. The structural deformation is mainly two-dimensional and shows only one main curvature in bending direction. Therefore, a fine mesh with linear solid elements of penta-6 type follows very well even local three-dimensional deformations at the impact spot where the glass window pushes through the ceiling lips. Let's have now a look on the third very complex application. The model of the V-fender was presented first in 2007 by Dr. Shimosono on a project conference in Whistler, Canada. His former studies, together with some tests, were done during his engagement at MSC Software Consulting Division. Today he is my colleague at INTES Japan, and with his courtesy I can make some comparisons between my studies with PERMAS and his studies with Mark and tests later on. The mechanical task here is shock damping. Fenders are mounted on harbor quays to absorb the shock of ship landing. For the simulation, a quarter model is used with two symmetry plane boundary conditions. To stiffen the rubber material during loading, there is a steel inlet in the fender near the fender bottom. We consider normal contact between fender bottom surface to supported quay wall. The mounting with screws is realized by suppressed surface nodes. Normal contact between ship and fender top is used for prescribed loading. The top plane is moved vertically towards the fender to simulate the ship landing. During the course of deformation, additional normal contact is considered between fender top surface and side symmetry plane, as well as self-contact for the fender inside surface. Here's some more details to model dimensions. The overall height is 100 mm, so 1 mm displacement corresponds to 1% compression of the fender's height. The hyperelastic material is considered as neo-hook type material law, again with two parameters for strain potential. In this simulation I used linear tetrahedron elements with medium edge length. Coming to the results. Again, let's have first a look on the macroscopic reaction force compression curve. At the beginning, we see a continuous increase in reaction force to a first maximum around 28% compression. Between 28 and 32% compression, the structure loses stiffness rapidly. Let's say the capability to resist breaks down. Buckling and folding effects can be seen, affecting contact force distribution vice versa, and enlarge the amount of strain. Therefore, smaller time increments are considered. After these effects are finished, the reaction forces increase again. Please have now a look on the development of displacements and deformation. The left view from outside to see the expansion of the structure and rotation of the top surface. And the right view is from inside to see the folding of element surfaces with active self-contact. The value of compression has a value in millimeter, so we have nearly 50% at the end. And you see in the right animation the folding is very heavy and we get a difficult contact situation. Also on the outside surface you get large strains. The turning of the top surface to the side. Therefore we have defined contact in the symmetry plane. Have a look on the total strain and recognize the high amount of strain. See here the development of total strains. And see here the development of contact and reaction forces in this slide. On the top surface you see the contact becomes smaller and with only few vectors, and the surface is rotated into the symmetry plane. The structural deformation of the V-fender is extremely three-dimensional and shows large curvatures and even folding of element surfaces during loading. The selected prescribed displacement leads in high loaded zones to an overall local element strain up to 300%. High strain increments occur if the load step is too large. Only a mix of manually selected medium to small time steps between 1 and 0.1 mm leads to a medium incremental growth rate for total strain and shows good accuracy and fast convergence. To calculate zones of buckling and surface folding is very complex and extremely sensitive to time step size. That means large strain changes should be controlled by time steps manually. An automatic refinement of time steps fails because localized stress strain effects together with distorted element shapes or the large curvature change on structure surfaces or rapid contact partner changes cannot considered yet in a global rule. The simulation process might still fail at the end caused by these effects. In addition to my studies, I want to show you a comparison between tests and simulation results. The comparison is not perfect because test specimen and even simulation models differ in many details, but maybe it makes clear the complexity of the mechanical challenge. On the left, you find the force compression diagram with 3 test curves and a mark and PERMAS result curve. And you see deformed structures for a test specimen above. The PERMAS results in the middle and mark results on the right side. Both analyses were calculated without friction and seems to be quite similar. Differences to the tests are obvious and need a separate discussion to assess the influence of material parameters, model dimensions, boundary conditions, etc. Coming to the conclusions of my studies. 3 realistic applications were analyzed and presented. Geometry and contact geometry updates were considered. Hyperelastic material was considered with medium and large strains. Large deflections and distortions of elements occurred during loading. A global decline of reaction force was analyzed. To carry out a nonlinear analysis needs advanced nonlinear PERMAS modules, deep understanding of the structural behavior of your model, appropriate element types, a suitable mesh discretization, and load-adapted time steps, a serious look on displacements and deformation results, as well as an assessment of contact and strain development, and last not least, step-by-step learning. Take advantage of nonlinear analyses to improve your component design. Thank you for your attention.